Welcome back to the deep dive. Today we're doing a systematic expedition into one of the most chemically fascinating columns on the periodic table.
Group 2, the alkaline earth metals.
Exactly. We're going to move beyond just the basics to really, quickly distill the most important concepts about beryllium, magnesium, calcium, strontium, and barium.
Focusing on those core principles that govern their behavior.
And before we even look at the atomic structure, let's think about why this group matters so much in the real world. I mean, think about military decoy flares. When you see those, you are seeing group 2 chemistry right in action. They use this finely powdered magnesium.
And the reason it's a powder is key.
Right. The huge surface area lets it react with oxygen just incredibly fast. It releases the detection systems on missiles.
And that utility, it goes way beyond just defense. Look at our infrastructure. The cornerstone of construction all over the world is calcium carbonate, limestone or marble. We harvest it, we roast it in these massive kilns to make calcium oxide. And that is the essential ingredient for cement. Quite literally built on group 2 compounds.
And it's not just construction, it's agriculture too. Farmers use slaked lime, which is just calcium hydroxide.
Right, to neutralize acidic soil.
Yeah, it's a basic substance. They spread it to balance the pH so crops can actually grow.
Yeah.
It's simple acid-based neutralization, just on the scale of an entire field.
So our mission today is to follow these elements down the group, from magnesium down to barium, and really understand the core systematic trends.
Okay.
We need to be able to predict what happens based on where they are in that column. Specifically looking at how their physical size changes, how that size dictates their reactivity, and how their key compounds, the oxides, hydroxides, sulfates, how their solubility changes as you go down.
Okay, let's start with the absolute fundamentals. What makes them group 2 in the first place?
Well, fundamentally, it's all about their electron configuration. Every single element in this group has 2 electrons in its outermost subshell.
So they all have that shared characteristic.
Exactly. 2 electrons just, ripe for removal.
And when we look at their physical size, what chemists call the metallic radius, how does that change as we move from top to bottom?
The trend there is very clear. The atomic size, the metallic radius, it increases as you go down the group.
And that radius is just a measure of how big the atoms are when they're all packed together, right?
In that giant metallic lattice.
Wait, why is that, though? If you're moving down the table, you're adding protons. The nuclear charge is getting stronger. Shouldn't that pull the electrons in tighter?
That is the classic counterintuitive point. And you're right, the nuclear charge does increase, but the outer 2 electrons are housed in a brand new principal quantum shell with each step down.
A whole new layer.
A whole new layer, and these new shells are significantly further away from the nucleus. And crucially, the increasing number of inner electron shells acts as a really effective screen or a shield.
So it blocks the pull from the nucleus.
It does. The distance and the shielding effect, they just win out over the increasing charge.
And that structural change, that must influence the bulk properties too. We see that the melting points, they generally trend downward as you go down the group.
They do, though magnesium kind of breaks that general rule a little bit, and density generally increases.
Because the mass is increasing faster than the volume.
Exactly. But the real consequence of that increasing size and shielding, well, that comes when we look at their reactions.
Okay, let's pivot to reactivity. We know these are reducing agents. They want to lose those 2 outer electrons to form a stable 2+ ion. But the crucial trend is that reactivity gets significantly more vigorous as you go down the group. Why is that?
It all connects back to the ionization energy, the first and second ionization energies. So the energy you need to pull off those 2 electrons, that energy decreases as you move down the group.
I see. So it takes less energy to rip the electrons off barium than it does off magnesium?
Precisely. Because the atoms are larger and the outer electrons are more shielded, they're just held less tightly. It makes them much easier to oxidize. And that defines the increasing reactivity.
We see this play out with dilute acids, right?
Absolutely. The general process is simple. Metal plus dilute acid gives you a metal, salt, and hydrogen gas. You put magnesium and hydrochloric acid, for instance, you get magnesium chloride, and you see bubbles of hydrogen.
But as you go down to calcium,
The rate of hydrogen production, the fizzing, it becomes visibly more vigorous.
and this is where we hit our first major chemical exception, and it's all about solubility, the sulfuric acid exception.
This is so critical. If you use hydrochloric acid, everything reacts completely. But if you switch to dilute sulfuric acid, the behavior just splits the group in 2. Well, magnesium reacts fine, because magnesium sulfate is really soluble in water. But once you get to calcium, the reaction it grinds to a halt pretty quickly.
So it's not that the metal isn't reactive enough.
No, not at all. It's very reactive. The problem is the product you're making.
So the moment the calcium starts reacting with the sulfuric acid, what happens?
You immediately form calcium sulfate. And this is key. The solubility of group 2 sulfates gets dramatically less soluble as you go down the group.
So calcium sulfate is the problem.
Right. It's only sparingly soluble. Strontium and barium sulfates are almost completely insoluble. So when the reaction starts, that insoluble calcium sulfate forms a solid white coating, a protective layer, right on the surface of the metal.
And that blocks any more acid from getting to the metal underneath.
Exactly. It's a phenomenon called passivation. The reaction basically seals itself shut.
That is a fascinating example of solubility just stopping a reaction dead in its tracks. So if we use barium metal and sulfuric acid, it would react for a split second and then just stop.
A fleeting moment,
Yeah.
and then it would be covered in a thick, inert layer of barium sulfate.
Yeah.
That trends sulfate solubility decreasing down the group. That is one of the 4 defining characteristics you have to remember.
Okay, let's move to how they interact with air and oxygen.
All group 2 metals burn in air or cure oxygen to form these white solid oxides. And these oxides are all basic in character.
Like that classic bright, blinding white light you get when you burn a magnesium ribbon in class.
That's the one. And the reactivity with oxygen increases down the group. So much so that barium metal is so reactive it actually has to be stored under oil to stop it from reacting with the atmosphere.
Wow. And what about the fun colors they make in a flame?
Ah, the flame tests. The heat from the burner excites the atoms. They quickly oxidize to the stable 2+ ions, and as those excited ions drop back to a lower energy state, they emit light at very specific wavelengths.
Which we see as color.
Okay,
for everyone listening, let's lock these in. Calcium gives you a beautiful brick red color. Strontium is a scarlet red.
A deeper red, yeah.
And barium produces a very distinct apple green color.
You got it. And these basic oxides that are formed, they're easily neutralized by dilute acids to form a salt in water. Solid magnesium oxide plus hydrochloric acid gives you magnesium chloride in water.
But if we use sulfuric acid on these oxides, would that sulfate problem pop up again?
Yes, potentially. With a solid calcium oxide powder, that decreasing solubility of the sulfate means that even if it's finely divided, a solid calcium sulfate layer can still form and hinder the reaction.
So you'd have to keep stirring it really aggressively to expose new surfaces.
Right.
Okay, moving on. How do these elements and their oxides interact with water? Let's start with the metals themselves in cold water.
Magnesium is, well, it's notably sluggish. It reacts very, very slowly with cold water to make magnesium hydroxide and a little hydrogen gas.
But with steam, it's different.
Completely different. If you swap the cold water for steam, the reaction becomes highly vigorous, exothermic, and instead of the hydroxide, you actually get magnesium oxide, that white, solid, and hydrogen gas.
Okay, so calcium then, it steps up the game a bit.
It does. Calcium reacts much more readily with cold water than magnesium does. You get a steady stream of hydrogen bubbles, and this cloudy suspension forms.
And that cloudiness, that's the slightly soluble calcium hydroxide, what we call lime water.
Exactly.
Yeah.
And as you keep going down, the reactivity with water continues to increase until you get to barium, which reacts pretty vigorously with cold water.
Now, what about the oxides reacting with water? Because this brings us to the second crucial solubility trend.
Right. When you mix the metal oxides with water, they form metal hydroxides, which can dissolve to create alkaline solutions.
Okay.
And if you take calcium oxide quicklime and mix it with water, it's not just a reaction, it's an event. It's extremely vigorous, highly exothermic. So much heat is released that the water can actually boil off and the solid lump expands and cracks open.
Wow. And the hydroxides that are formed, the XOH compounds, they follow a solubility trend, but it's the exact opposite of the sulfates, isn't it?
It is. And this contrast is probably the most important takeaway of all of Group 2 chemistry. The solubility of the Group 2 hydroxides increases as you go down the group. Magnesium hydroxide is barely soluble at all, while barium hydroxide is the most soluble.
So the practical consequence of that is that the solutions get more and more alkaline as we go down the column.
Precisely. If you look at saturated solutions, magnesium hydroxide solution is, mildly alkaline, maybe a pH of 10. Calcium hydroxide or lime water is more basic, around pH 11. Barium hydroxide solutions are the most alkaline.
Because more of it can dissolve, so you get a higher concentration of hydroxide ions.
That's it.
So back to the farming example, when farmers use calcium hydroxide, they're using this property. It's soluble enough to work in the soil, but not so soluble that it just washes away in the first rain.
That's right. And speaking of neutralization, if we react these hydroxides with an acid, that's just a standard neutralization reaction.
But wait, if we use sulfuric acid on, say, barium hydroxide solution, we'd still see that sulfate solubility trend, wouldn't we? Even in solution.
Oh, absolutely. The moment those aqueous barium ions meet the aqueous sulfate ions, you get this dramatic, immediate formation of a white precipitate.
The highly insoluble barium sulfate.
Mm-hmm. It's a classic qualitative test to identify sulfate ions in a solution.
Okay, finally, let's wrap up with the carbonates and how they respond to heat.
Okay, so all the group 2 carbonates are insoluble in water. They react with dilute acids to give salt, water, and carbon dioxide gas. The fizzing test for carbonates.
Right.
So reacting magnesium carbonate with sulfuric acid works perfectly because the magnesium sulfate you make is soluble. The reaction goes to completion.
But let me guess. Let's return to our old solubility problem one last time. If you use calcium carbonate or barium carbonate with sulfuric acid,
The reaction quickly halts again.
the protective layer of insoluble sulfate strikes again.
Exactly. That insoluble layer forms on the surface of the solid carbonate. It prevents the acid from getting to the rest of the compound, and the carbon dioxide fizzing just stops.
Okay, so let's talk thermal stability. What happens when we heat them? When we heat these carbonates, what happens?
When you heat them strongly, they decompose into the solid metal oxide and carbon dioxide gas. So, for example, heating calcium carbonate gives you calcium oxide and co-uro.
And what about the nitrates?
Their nitrates also decompose when heated. That process is a bit more complex. It produces the metal oxide, oxygen gas, and notably, this toxic brown gas nitrogen dioxide, NOO. That brown gas is a key signature of nitrate decomposition.
And this leads us to our final systematic trend for the group. Thermal stability.
Right. The temperature you need for the thermal decomposition of both the carbonates and the nitrates, it increases as you go down group 2.
Meaning that barium carbonate is much more resistant to heat than magnesium carbonate is.
Far more resistant. The lower down the group you go, the more thermally stable the compound becomes.
This has been a really complete systematic walkthrough of the alkaline earth metals. Let's just quickly synthesize the 4 defining trends that govern their chemistry as we move down the group from, say, magnesium to barium.
Okay, let's do it. First, reactivity.
Mm-hmm.
It increases because the electrons are easier to remove.
Got it.
Second, hydroxide solubility, and therefore the alkalinity of the solution, that also increases.
Okay.
Third, sulfate solubility goes the opposite way. It decreases, and that leads to that critical passivation phenomenon.
Right.
And fourth, the thermal stability of the carbonates and the nitrates, that increases. They get tougher to break down with heat.
Those 4 points really crystallize everything. We've seen how solubility is really the arbiter of chemical fate here, right? It causes calcium metal to stop reacting with sulfuric acid, but it allows calcium hydroxide to neutralize huge fields of acidic soil. So that leads to one final thought for you to chew on. If we consider beryllium, which is at the very top of the group, its compounds would tend to be extremely soluble, while bariums are often insoluble. How would that extreme difference in solubility between beryllium and barium affect their environmental persistence? Think about which one would be more easily absorbed or washed away by groundwater.
The application of those solubility trends really dictates their entire story, whether they stay put or just dissolve away.
Until next time, keep digging deeper into the periodic table.